Okay, ladies and gentlemen, welcome to the 7th Bridging Transportation Researchers Conference. And you're in the Eastern track, section 4, shared mobility and micromobility systems. Let me introduce myself. My name is Xinping Guan. I'm a professor at the Harbin Institute of Technology in Shenzhen, China. I'm also a researcher. I was working with Professor Moshe Ben Akiva at the Massachusetts Institute of Technology. So it's an honor for me to be your section chair for the next 2 hours. Yeah. So today we have 5 great presentations centering around this topic of shared mobility and micromobility, as you can see on the screen. So dear presenters, please kindly make your presentation within 15 to 20 minutes. And at the end of each presentation, we'll have a brief Q&A. So coming up first, we have Mr. Yikang Wu. So he's also today's our Zoom coordinator. Thank you, Yikang, for supporting us. And First, let's give a round of applause to Mr. Yikang Wu. He will discuss about his research with us. Without further ado, the floor is all yours.
Thanks, Gina. And hello, everyone. And yes, as Gina said, I'm also your Zoom coordinator today. But it's a great honor for me to be here to present our work on the choice modeling about the micromobility usage behavior. So I'm from the University of Queensland, and my supervisors team are Dr. Mehmet and also Professor Zudo. So first of all, let me introduce our study. So as you can see here, nowadays the great major part of the trips are taken by the private vehicle or the public transport, and very late of them are taken by active transport. However, we are thinking the benefit of the electric micromobility, this active travel mode, they can bring by taking the role of the private car and public transport. So for example, by replacing the usage of private vehicle, it can free up the road and park space, and there's no running emissions as they are electric, right? And by complementing the usage of public transport, it can be seen as a way to deal with the first and last mile problem, and also improve the coverage and accessibility of the PP network itself. However, there are several benefits and also come with some challenges. So what are the, how can we, simply speaking, how can we boost the mode choice behavior of using electric micromobility? So first challenge is, what are the most influential factors that shaping their mode choice behavior? And we should recognize that there should be some heterogeneity existing among the population regarding their behavior choice. But how much is that? How much is that heterogeneity? And how can these insights to be to inform the effective policy measures to promote the adoption at the end of the day? So to fill up this knowledge gap, we designed and conducted a stated preference study. So the key idea here is we designed an online survey to collect the stated preference mode choice data from the participant. And in our study, we recruited more than 1,600 participants that are Brisbane city residents. We make sure the representative sampling by quoting the age and gender percentage of the city, Brisbane city itself. One particular restriction of our participant is their age should be over 16, which is the minimum legal age for them to ride a personal mobility device here in Brisbane. And this is the structure of our questionnaire. So basically, it has 4 parts. First of all, we explain our study, and then we collect some reviewed choices questions. And the third part is the key part as well of our survey. So which is the choice experiment. During like in this part, we will present several scenarios, and ask them to state their choice preference. And the last part, we're gonna also collect some social demographic information for further analysis. How, talking about the part 3 I just mentioned, so how we set the mode choice scenarios. So basically speaking, instead of we just come up with some fully hypothetical scenarios, we will let participants to reconsider their mode choice for one of the reference trips. So we define the reference trip as this one. So basically speaking, the last trip within the range of 3 to 30 kilometers. And we include both car users and PT users. So car users and PT users are the participants who said they use car or public transport for their reference trip. And for each participant, they will be presented with 6 scenarios. And at the end of the day, we collect the data from over 1,000 car users and over 400 PT users. And so how we present several alternatives under each scenario. So first of all, their reference travel mode, the status quo, which could be car or public transport, and 2 electric micromobility related alternatives. One is the combination, the multimodal trip, combine shared micromobility with public transport, like what is illustrated here, and the personal micromobility usage, which is illustrated here. So yeah, this is kind of the illustration of our scenario setting. And this table basically present all of the attributes and attributes level of our stated preference studies. And we apply the D-efficient experimental design to make the choice scenarios more realistic and more efficient for the further model estimation. So basically speaking, we have several reference value and base value, and all of those, we want to make sure all of the values, attributes levels are as realistic as possible. So we employ these reference values which come from the Google Maps API, and also may come from OpenStreetSurvey API to get the as realistic as possible values of all of those attributes. And this is an example scenario of our experiment. So they're gonna have a trip scenario, the travel distance, the weather of the trip, and they will be presented with 3 alternatives, as I mentioned before. And they will have some, there will be several attributes to describe each alternative as well. So they're gonna state their choices, which traffic mode will be their top pick and what will be their second pick. And right now we have this choice behavior data from real world. So how can we get the insight all of those data? So there are going to be several choice models, and in this study we estimate the latent class choice model, which has such a structure. So it's kind of an iterative framework that we assign all of the participants to several latent classes, and then we estimate the class specific choice model, and then we test the model based on observed choices, and then we just testing them with the growth truths. And at the end of the day, it will be iteratively updating to get the best model performance, which is shown as here. So one of the significant parameter of the latent class choice model is the number of the segment, so which should be specified by the researchers. And for this study, we have these 2 like testing process for both car users and public transport users on the number of the segments. And the criteria, one important criteria as shown here is BIC, which can tell you the balance between the number of parameters and the performance of the model itself. So the lower the better. at the same time, if there's a rule of thumb that if the segment become quite small, then we just stop the testing process on the number of segments. And here you can say when it comes to the 4 segments, we will observe a really small segment, which only contain around 10% of the participant, which cannot give us a stable estimation. So at the end of the day, we estimate the 3-class model for car users and 2-class model for public transport users. And based on this model, we also get the prediction of their choice probability for each segment. And the interesting thing is for both car users and public transport users, we can observe one specific segment that can be defined as micromobility resistant. That majority of them will just stay with their original choice, the status quo choices, status quo choice, but not opt to the micromobility alternatives. And these are several statistical values estimated from our model, but it's not that easy to be conveyed and explained. So instead of looking at all of those numbers, we are going to, one thing is I want to show that is within our model, as you can see from all those star signs, majority of the attributes will be tested as significant, and which can also prove the performance of our models. But talking about the explanation of the model, there are gonna be some more interesting insights instead of just looking at the numbers. So first of all, if I have a look at the latent class profile for car users here, we can see for gender and age groups, there are significant differences between segment 2, the resistant class, with other 2 EMM leaning groups. For example, there are more females in the resistant group, and the age group is much more elder in the resistant group compared to other 2 supporters group. And at the same time, we can see that the income is lower as well for the resistant class, and the dramatic trend we can observe from the micromobility experience that for the segment 2, the micromobility resistant group, the majority of them do not have the previous micromobility experience. But for the other 2 groups, we can see that the majority of them do have the experience on micromobility before. And sorry that the resolution here is not that high, it's not that clear, the figures, but still we can observe the similar trend here that the resistant group are more female and elder people for public transport users as well. And they have lower weekly income, and they had very little micromobility experiences compared to the micromobility adopter, the potential micromobility adopter groups. From another perspective, if we have a look at the living suburb probability distribution of both car users and PT users. So during the survey, we also collect their living suburb information, and which give us such an interesting insight that the micromobility resistant are like more evenly distributed across the city. So this is the Brisbane city, but for segment 1 and 3, majority of them densely living in the city area. So and similar trend can be observed for public transport users. So micromobility resistant groups, they are more distributed evenly across the city, but majority of the potential adopters just live in the city area. So it's easy to be explained that like especially for the public transport users, their usage of micromobility may highly depend on the coverage of the public transport network, which is densely in the city area. And from all of those data and insights and visualizations, how can we get the practical policy implications? So first of all, we want to say that we should improve the investment on dedicated micromobility infrastructure. As from the estimated model, we can find that the riding comfort is quite important to promoting electric micromobility usage, especially the bad weather, the rainy weather can prevent people from shifting to micromobility usage a lot. At the same time, this dedicated infrastructure can reduce travel time as well and can integrate with public transport infrastructure for seamless multimodal trips. And from the living suburb distribution analysis, we can see that we should prioritize the initial investment in urban area, which is more effective. Meanwhile, talking about the shared micromobility alternative, we should introduce several like public PT plus shared micromobility usage bundles, as they are more travel cost sensitive. And yeah, because potential users groups are more cost sensitive compared to travel time. At the same time, we can upgrade public transport timetables to support the existing multimodal users. And from the inside of the class profile, we can see that the pilot discount could be applied for young full-time city workers, as they are more they hold the more potential to accept such a alternative. Last but not least, we should boost electric micromobility adoption through hands-on experience. As from the class profile, can see that the previous micromobility experience play a significant role on their choice behavior. So if people have such previous experience, they are happily to shift their carbon mode choice from whether car or PT to electric micromobility usage. So from this perspective, we should provide some free EMM trials to specific target groups from the inside of our class profile analysis. At the same time, we can also run some shared micromobility compliance around public transport stations to further support the shared micromobility usage. And thank you for your attention and time, and I'm more than happy to answer any questions.
Okay, thank you, Yikang. And let's see, in the audience, do you have any questions about Yikang's presentation?
Not yet, but yeah, if anyone has problems, they can post in the chat box later on. I'm happy to come back to answer their questions. Yeah, I got one. I was wondering why you focus only on electric micromobility and not micromobility in general, with electric being a part of it. Yeah, that's a great question. So first of all, we are not intentionally to be only focused on electric micromobility, but not the other micromobility usage, because the reason is currently in Brisbane City, and I believe in majority part of the world, that the micromobility devices are, majority of them are powered by electricities, and we want to say that compared to conventional bicycles, the electric micromobility have some further benefits that the riders can pay less. So it's easier for riders to ride, and I think here, especially here in Brisbane, we got a huge hilly environment here in Brisbane. The elevation could be some factors that prevent people on this reading experience. So in this study, we just seeing that, okay, for how about we just focus on electric micromobility, because there's more, the benefit is more pronounced and maybe more attractive if we say it's electricity powered. But yes, I think the micromobility in general is a more broader background, and I believe the choice behavior should be some similarity between the electric micromobility and the micromobility in general. But there should be some tiny difference between them. It could be a very interesting topic which can be studied in the future. But yeah, at the moment for this study, we focus on the electricity powered micromobility, like e-bike and e-scooter. Yeah. And I got another one. I'm wondering is that it's more focused on would the shared USB different, or should e-scooter can be taken on board? Yes. It's another very great, brilliant question. I would like to say so. In short, our study also focused on shared micromobility. If you have a look at the, sorry. If you have a look at this one, so this PTSMM is a combined multimodal trip with public transport here. This segment, for this segment, which is defined as the usage of shared micromobility, for example, shared e-scooter here. We want to try to find the difference on usage patterns between the shared micromobility and personal micromobility as shown here, which is also one of the focuses of this study. And we do find some several differences, such as that for shared micromobility, people are more cost sensitive, and for personal micromobility users, they are more travel time sensitive. That's also because the current pricing scheme for shared micromobility is a little bit more expensive, as you may know, because you are also from Brisbane. And the scooter can be taken on board on trains. That's a very interesting topic. And I think there should be, but for this specific usage pattern, the experiment design should be different if we want to look at the choice pattern on specific e-scooter on train, this kind of usage. But for this study, we don't look a lot on that. But that's a very interesting study, and I think in Australia there should be some teams working on that. Yeah, I know there should be a project from iMove. They are working on this kind of behavior. Yeah, and absolutely they're gonna boost the usage of shared micromobility, like the e-scooters, this personal mobility device. And maybe for last question, how do you determine your class membership model has been successfully constructed? Is it through the result? Yes, I think so for latent class choice models, the number of classes is a parameter that the researchers should play with, as you can see here. So basically, we just determine the number of segments by looking at the performance of the models with different number of segments. So we tested the latent class choice models with different numbers of segments, and by looking at their performances, I would personally recommend looking at the BIC criteria, which can give you a great balance, can tell you the balance between the number of parameters and the performance of the model. So with the increase of the number of parameters, in other words, you are going to have the risk of like make your model more complicated, and but the log likelihood, this is the performance of the model. You want to get a balance between these two parameters, and the BIC is a criteria which can tell you this balance. Another criteria is what I mentioned before, that look at all of the segments, the percentage of all of the segments. If they're going to be a segment with very tiny portion of the participant, for example, here for 4 classes models, there's one class only take around 10% of the participant, which can be seen as a tiny class. And with this small number of the participant, you cannot assume that your model can give you a stable estimation because the observations are so limited. So it can be the rule of thumb is that when it comes such a small group, you should stop your testing on the number of segments. So you should just stop here by 4 segments and do not go further. Yeah, I think that's pretty much about the Q&A. Thanks.
Thank you. Thank you very much. And then with that, let's move on to the next speaker today. Kat Sui from the University of Hong Kong. Can you hear me?
Thank you. I'll share my screen.
Sure. The stage is all yours.
Yes. Can you see it? Can you see my screen? And
Yes, all good.
yes, thank you. So thank you, everyone. I'm Jia Cui, and I will introduce one of our topics about the repositioning and the battery swapping strategies for electric bike sharing system. And this project is co-worked by with Professor Sito and Dr. Wang from Hong Kong U and HUST. And next, what's the matter? Sorry. Oh, next I will follow this outline to introduce our work. And first of all, I will introduce the background and some motivations of this study. The shared micromobility, including the shared bikes, e-bikes, and e-scooters, works as an essential transportation mode in the first and last mile urban trips. In the US and Canada, the ridership has increased by 40% in 2023, surpassing the pre-epidemic peak in 2019. This increase is mainly driven by the continuous expansion of station-based bike sharing systems. And according to NACTO, 40% of which are the e-bike trips. So we can find that electric bike sharing systems have gained widespread popularity. It's compared to the private fuel-powered cars or buses, it is much more eco-friendly. And especially in the traffic jam, it provides flexible choices. And also, it is operated by one-time rental pay. Therefore, people no need to pay for the high cost for the purchasing of the private electric bicycles. So more and more service provider of bike sharing systems have deployed e-bike sharing in their systems. For example, the Lyft and Lime in the United States, Didi and Meituan in China, and Waymo both in European countries. Compared to the traditional manpower bikes, the electric bicycles are also can be found, returned, and rent through an mobile app. But differently, it travels faster and cover longer distance without consuming a lot of labor. And it is also affordable for almost everyone. So many of us may be the users of shared bikes. But on the other hand, the e-bike sharing systems suffered from the imbalance between the supply and demand in the long term. and it also needs regular charging to ensure the availability. So we have to design the risk distribution scheme to solve the unbalance and charging issues. And this process is known as the bike repositioning problem. It has been well studied and numerous branches have been explored. In this study, we only focus on the vehicle-based static bike repositioning problem. The simplest form of this class is a variant of VRP problem, which is NP hard. So the VRP problems studied today are all at least NP hard. According to the literature review, we find that compared to the previous traditional BRP studies, the study involving battery swapping strategies for the e-bike sharing systems remains limited. Among above literature, we find 2 studies incorporate the battery swap into the bike repositioning process, but we still summarize some differences and research gaps. First of all, we different from Zhou et al. In 2003 in operating strategies because Zhou et al. Separates the 2 options using the different fleets. This will bring some additional cost, and we think that the 2 tasks has some interplay because through battery swapping, the depleted low battery e-bikes can be recovered into usable, and we should take these 2 tasks together using the same fleets. And also, our study is different from Xu et al. In 2022 on the allocation of batteries in the vehicle. Xu et al. Allow half of the vehicle capacity for the batteries, but this is not very realistic because the number of batteries we carried from the depot should determined based on the status of the system and the demand. So we set the capacity for the batteries in the vehicle as a variable. Therefore, we summarize several research gaps, including no study focus on handle this 2 tasks into one problem, and we also find that many study overlook the impact of service failure in the unsatisfied dock demand. To fill in this gap, we propose a new multi-vehicle e-bike repositioning problem. And in our system, we have a set of stations and 1 depot. There are 2 types of e-bikes in our system. One is usable, another is low battery. And we allow a fleet of homogeneous vehicles to do the rebalancing. Each vehicle depart from depot and travel among the station to do the bike relocation and battery swap simultaneously, and finally the vehicle return to the depot within the time budget. To formulate this problem, we proposed an MILP model using the arc-flow method, and these are the parameters, sets, and variables we defined. For the objective function, we aim to minimize the total repositioning cost, which includes the penalty cost of bike and dock deviation, and the fixed cost of the vehicle usage, the travel cost, and the operation cost. We guarantee that each station can be only visited by all the vehicles only once, and we ensure the inflow and outflow reservation. We also limit the number of vehicle use is not exceed the fleet size. We also eliminate the subtour. We guarantee that the each station and each vehicle is not exceed its capacities. We also update the repositioning time to ensure the total repositioning time is within the time budget. Finally, we did sensitivity analysis in small-scale networks to explore some properties of our problem and validate the correctness of the model. First of all, we explored the effect of involving the battery swap operation into the bike repositioning process. We compare two cases with and without battery swapping. We found that there is an apparent decrease when we including the battery swap into the bike repositioning process. That means that the battery indeed required less vehicle capacity than electric bicycle. So the more bikes can be transferred and distributed among the station. Meanwhile, we find that the battery swap reduced the traditional relocation time, and it is more time saving to directly transfer depleted low battery e-bikes into usable. And next, we investigate the effect of different unit time for loading and battery swapping. There are 5 cases. The first one works as the baseline, and the case 2 and 3, into case 2 and 3, both tasks takes longer or shorter time. And in case 4 and 5, one operation takes 10 seconds than another. And each case corresponds to the real life scenarios. So according to the results, we find that in case 2, there is an increase in the bike division cost and decrease in the loading cost, as less works can be finished within the same time budget. And on the opposite, in case 3, more rebalancing tasks can be done, and therefore enhancing the whole demand fulfillment. In case 4, fewer bikes can be relocated when the unit loading time is increased, which also affect the time, the demand for bike. But in case 5, when the unit battery swapping time takes longer, there's only a slight increase in the bike duration. Therefore, we deducted that although we include the battery swap into the bike repositioning process, the system still rely heavily on the bike relocation. So both operations are essential for the balance of the system. Finally, we test the effect of different vehicle capacities. We increased the vehicle capacity from 5 to 40, which is a very high level. And according to the results, apparently, larger vehicle capacity can allow more bikes and batteries transferred among the system, and therefore the total repositioning cost is reduced. And when we reached 30 to 50 to 40, the total repositioning cost is not reduced anymore. But more interestingly, we also find that the marginal benefits of this reduction is reduced as the vehicle capacity increased. That means that if we consistently increase the vehicle capacity for this task, it is not very cost effectively. So in summary, we proposed a novel e-bike repositioning problem to minimize the total cost, and we formulated this problem to an arc flow model. And we explored various properties, including the involving the battery swapping, different unit time for loading and battery swapping, and the effect of vehicle capacity on the total cost. And also we have some ongoing works, for example, comparing the detailed strategies between our strategy and the previous one. And we also designed a hybrid method to tackle the problem in large-scale networks. And according to the time limits, I can't exhibit all of that. And thank you for listening. Thank you.
Thank you, Jia. Any questions for her? Any thoughts and comments? Feel free to unmute yourself, or if you want to type on the screen, if you want to type on the chat box, that's also okay. Any thoughts, questions?
Sorry, I think they cannot unmute themselves because I disabled them. But
Okay.
feel free to text in the chat box.
Yeah. All right, I don't see any questions in the chat box, but that's okay. So with that, thank you very much, Jia. Thank you for your presentation. We will move on to our next presenter. Coming up next, we have Shunta Kochi from University of Tokyo. Can you hear me, Shunta?
Yeah, thank you. I can hear you. Can you hear me?
Yep, we can hear you.
Thank you. Okay, I'll share my screen. My name is Shunta Koch, and I'm a master student at the University of Tokyo. Wait, sorry. I'm sorry, maybe the recording has started. I don't know. Sorry.
Do you want me to play your video on my side?
Sorry. Maybe I have recorded the my presentation with this PowerPoint. So if I start a slideshow, this record will start, and I don't know how to solve it. So maybe I can use another slide without any record.
Is it the one you want to share? If you can see the screen, this one.
Oh yes, this is the one I want to share.
This like around 10 minutes recording. Is that the one you want?
Yes.
Cool. Then I can play on my side.
Okay. I'm sorry. Then I want.
All right. Just be ready for the Q&A after the presentation. That would be all good.
Sorry. Thank you. Good afternoon, everyone. My name is Shunta Koch, and I'm a master student at the University of Tokyo. Today, I will present our study titled Exploring Shared Bike Utilization Patterns and a Prediction of Availability Status in Japanese Cities through Machine Learning. This research was conducted jointly with Professors Takami, Paradi, and Luo. Let's start with some introduction of this research's background. In recent years, bike sharing has become increasingly popular as a sustainable form of urban transport. However, many systems face issues such as unbalanced supply and demand across stations. This leads to user dissatisfaction and increased operational costs. Therefore, our goal is to predict when and where bikes will run out or stations will become full, and to explore the key factors behind such imbalances. Many previous studies have focused on forecasting bike rental demand using statistical and machine learning methods. While these models compare prediction accuracy, few have focused on analyzing why availability changes. In our research, we defined a station-level availability ratio, that is, available bikes divided by station capacity, as a target and call a ratio. We use clustering to identify usage patterns and classification models to predict future availability status. This allows us to better understand both system behavior and influence factors. Here, we summarize our primary data sources. First, the BSS and OD data was used for clustering and constructing availability prediction model. BSS means the bike sharing systems. The table below illustrates a sample of the ratio in BSS data. In addition to BSS and OD data, we used weather data and location data for input features of availability predicting model. Here are a summary of data which we used. The overall workflow is depicted here in 6 steps. First, we perform EDA and pre-processing across all 3 datasets, BSS, meteorological, and locational data. Checking for missing values and outliers and perform necessary clearing. Next, we apply k-means clustering to uncover typical availability variation patterns. In addition to clustering, we construct availability predicting model. We constructed model inputs by generating relevant features from the raw data. Steps 4 and 5 involve training multi-class classification models with k-fold class validation, then tuning hyperparameters to optimize performance. Finally, we interpret model outputs using SHAP and PDP to understand key drivers of availability. Next, I'll talk about clustering analysis. We first cluster all 479 stations by their ratio at 3 a.m., splitting them into 2 sub-datasets. Each subset in this is then clustered again based on its full time series, yielding 4 final groups. Cluster 1 shows low availability early morning and high at night, typically commute hubs. Cluster 2 remains low throughout the day, often retail or mall day areas. Cluster 3 stays high all day but sees low usage, underutilized locations. And Cluster 4 peaks early morning and dips at midday, residential neighborhoods. These figures are the visualization of clustering results. The left panel plots the average ratio and rent return counts for January 9th for each cluster. I extracted a single day for this presentation, but the trends which we can see in this figure was almost the same in all periods. You can see Cluster 1's sharp evening returns and Cluster 4's morning rentals. The right map shows the spatial distribution. Blue and orange clusters concentrate near central business areas and event venues, while green and red clusters spread into residential zones. Next, we constructed availability predict model. To model station availability, we level hourly ratio into 3 classes, low, medium, and high. We assign these levels across all Chiba Prefecture stations' hourly ratio, then train a light GBM multi-class classifier. Light GBM was chosen for its high processing speed and strong accuracy on large tabular datasets. These are the features engineered for model inputs. Please refer to the slides for detailed information. We created a total of 49 features, consisting of 3 types: locational features, weather features, and time features. Next, we define our evaluation metrics. We use the F1 score, computed as the harmonic mean of precision and recall, to balance false positives and false negatives. In our multi-class setting, we compute an F1 score for each class and report the macro F1, the unweighted average across classes. We also display the confusion matrix, which is actually not a matrix but a helpful visualization of true versus predicted level counts. Here are our results on the train and test datasets. On the training data, we achieved a macro F1 of 0.92. However, on the test dataset, the macro F1 falls to 0.72, indicating overfitting. The accompanying conversion matrices show that the model sometimes confuses low and high availability classes more than medium. To interpret our model, we apply shape values, which quantify the average contribution of each feature to the model outputs. The violin plots on the left show the distribution of shape values per feature across all data points. Colors indicate the feature's actual value, red for high, blue for low. The bar plots on the right rank features by their mean absolute shape value, highlighting their overall importance for predicting each class. We used partial dependence plots for the model interpretation too. Partial dependence plots visualize how changes in a single feature affect the predicted class probability. For the low class, we see that increasing office density steadily raises the probability of a station being classified as low availability. Similarly, certain hours of day and seasonal factors shift class probabilities. For the high class, higher office density and educational facility can strongly decrease the chance of high availability. These plots help us understand feature response relationships. We can find that top 5 features in shape value are identical for both low and high classes. Office agglomeration, educational facility agglomeration, time of day cycle, and seasonal cycles. Office density contributes most to both classes. This confirms that station availability is strongly governed by the surrounding built environment and by daily and seasonal time cycles. Drawing on both clustering and predictive analysis, we infer 2 preliminary scenarios for supply-demand imbalance. One is stations serving commutes. Those near high concentrations of offices and schools exhibit pronounced morning and evening availability swings. Another is stations with consistently high or low availability, indicating permanently over or undersupply locations. Effective management should thus focus on commuter peak rebalancing and on resizing or resizing docks at consistently imbalanced stations. Despite promising insights, our model suffers from overfitting, suggesting the need of further refinement. Also, future work will include expanding feature types, for example, by adding residential rent density agglomeration and linking availability to real demand, since low availability alone does not always justify rebalancing if latent demand is also low. By quantifying latent demand alongside availability, we can more precisely target true supply-demand mismatches. Thank you for your attention. I look forward to your questions and feedback.
All right, thank you. Let's see if we have any questions or comments for this presentation. See, I do have a question about this actually. So you use the machine learning techniques in your study, yeah? So can you talk about the explainer, because you actually run some I think if you go to the sharp like that figure, you were able to use the machine learning techniques, but also being able to analyze some of the like influential factors. Was that the case, or can you talk a little bit more about that?
Oh, I'm sorry, I couldn't hear the last sentence.
I was asking about you use the machine learning techniques, right? So I also see some figures that where you were trying to analyze the influential factors, like what are the factors affecting your results? And can you elaborate about or talk a little bit more about like using the machine learning techniques? How is this process done? Or because I know like machine learning techniques are usually criticized because you couldn't know exactly what's going on in the black box, right? But it seems like in your study you use a technique to be able to at least give some insights about what are the factors. Can you talk a little more about that? Thank you.
Okay, thank you. Can I share my slide?
Sure. It's on your phone.
So I started to think about using the machine learning when I had a research for some previous research, and so yeah, I understand that there was more, how to say, like a model or like another measurement to analyze what are the factors influencing the availability of the shared cycle station. But I think like for this kind of big data, machine learning model was effective for analyzing it and also constructing a model with how to say, like computational time. And also I was really interested in applying the machine learning to this urban transportation field. So also that was my how to say, like reason for applying the machine learning model. And yeah, and also the reason why I used the light GBM was same to this kind of reason. I wanted to construct a model with uh, useful time, so I used the light GBM, which is really effective to constructing a model in high speed and with high interpretable thing. Yeah, that's the reason. Thank you for your question.
Okay, thank you. So let's see if we have any more questions in the chat. Okay, no, I don't see any questions there. And okay, so with that, thank you very much for your presentation. And we will move on to our next speaker, Runqiu Hu from the University of Hong Kong. Runqiu, can you hear me?
Yes, thank you. Can you hear me?
Yes,
Can
we
you hear me?
can.
Okay,
Yes,
okay.
please
So
share your screen
let me
and
share my screen. Okay. So can you see the screen?
Yeah, all good.
Okay. So thank you everyone for joining this discussion. My name is Renju Hu from the University of Hong Kong. So today I'm going to share with you my research on repositioning in bike sharing systems with broken bikes considering on-site repairs. So the work is conducted by me and my supervisor, Wang Sito, also from the University of Hong Kong. So the previous speakers have already given us quite a lot background on bike sharing system repositioning. To recall, let's just use this illustration graph to uh, talk about like what is bike repositioning problem. So overall, we have 4 users here, and 3 users want to go to station 3 for bike renting. However, there is no bike at that station, so they have no bike to use. This station is defined as a deficit station based on supply and demand. And for station 1, it is a surplus station as there's only 1 user, but 3 bikes are there. So to balance this demand and supply imbalance, the movement of bikes between stations is called bike repositioning problem. And this research has been extensively studied by a lot of researchers. However, let's consider a serious case here is like these two bikes become broken at station 1 after the bike has been moved to station 3. So the originally surplus station of station 1 becomes deficit, and the user has no bike to rent at the moment, and he is very likely to leave the system. So considering this problem becomes more complex, but it is necessary because the existence of broken bikes in the system is non-negligible. So how do we do with these broken bikes? Currently, there are two major modes of bike repairs. First is on-site repairs. You see the maintenance workers go on-site to repair the bikes, and the bikes becomes usable from broken at like a 5 or 10 minutes repair. The other one is the reposition trucks, which is this truck. They also carries these broken bikes when they do the repositioning across the stations, and they finally send those bikes to the depot to do a uniform repair. So as previous study has already found that repositioning schemes with long roads or heavy vehicle loads would produce more carbon emissions. So this is against the launch of the bike sharing system campaign. And incorporating on-site repairs could obviously alleviate the problem, as you don't have to carry those bikes, right? To prove that the broken bikes are non-negligible, we see the number of bikes repairs by year by city bikes from 2020 and to 2024 has went to a peak at 2022, which reaches approximately 600,000 repairs. I have to add that the decrease at the following 2 years is not because the problem becomes non-negligible. It's because city bikes became to launch a hybrid mode at the stations with both traditional bikes and e-bikes at the stations. So the usage of the traditional bikes is not that high, so hence the repair decrease. However, even for like 315,000, this number is still considerable. Hence, we propose our problem description. So in our problem, despite the traditional bike reposition, which incorporates like the trucks depart from depot with some initial loads of bikes, and then they collect usable bikes from station with surplus bikes, and they deliver the usable bikes to stations in shortage of bikes. Also, they could collect some of the broken bikes from the stations, and finally they return to the depot at the end of the repositioning horizon. So the start point is the depot. And meanwhile, like at the same time, a set of repairers, they also depart from depot, and they take their repairing tools and they repair the broken bikes at stations with broken bikes, and also return to depot at the end of the repositioning horizon. So we assume that the repairers travels with a tricycle, and the tricycle do not generate any emission. Also, the speed of the tricycle is proportional to the speed of trucks, but obviously it would be much slower. So each truck can visit an imbalanced station or a station with broken bikes arbitrary number of times. This is due to like the truck has a capacity. Sometimes some stations are in a huge deficit, like the truck cannot handle the problem, just visit it once, kind of like split demand in the VRP problem. And each repairer can only visit the station with broken bikes. This is also obvious. So each station with broken bikes can be visited by at most one repairer, and only once, because since the repairer went there, they have no point like just handle part of the repairs and then visit it again. So this is a simple illustration of the problem. So we see that the planning horizon is discretized into 12 periods, and we see station 6 is visited by both repairers and trucks, and the trucks collected 19 usable bikes, while the repairers repaired 8 broken bikes, and these 8 broken bikes becomes usable bikes immediately. So this is a multi-visited station. And also the truck is allowed to return to depot at the intermediate period because it's like the truck capacity is 20. So the truck is full at this moment. So he need to drop all the bikes on the trucks to save space for the subsequent visits. I'm not going too detailed on the model formulation because unlike the previous speakers, our problem incorporates multiple visits by multiple agents like trucks and repairers. So the classic arc index formulation is not sufficient for our problem because we need to track the inventory at each station and track the inventory on the trucks when we do the repositioning and the repairs. Hence, we discretize the time into time intervals with equal length. And this time matrix is then converted to a time period matrix by calculating using the rounding up divided by the length of each period. And so example is like we have a decision variable xijtk. Note that the superscript upright t represents the truck and the subscript t is the index of a time. So they're not the same t here. So this is a binary variable representing the route of truck K. If the K departs from I to J during period T, then it is equal to 1, 0 otherwise. So for this 0, 1, 3, 2, and back to 0 depot, we have these 4 variables equal to 1 and other variables equals to 0 for truck 1, yes. And the objective of our model consists of 2 parts. First is user dissatisfaction. The other one is the truck emission. So we first look at the second term. As you see the calculation of the emission, all these numbers are just constants, and Q is the truck capacity. The only 2 decision variable here is psi and D. So psi is the load of bikes on truck, and D is the travel distance. So basically, the load and the travel distance determines the emissions, right? So we need to make sure we can finish the work with smaller loading and shorter travel distance. And the first term, and these are some important constraints for the MILP model. So basically, like at each time period, the limits of the capacity of trucks cannot be violated. And also at the stations, capacity cannot be exceeded. And these trucks and repairers have to depart from depot and return to depot. And a station can be visited by repairers at most once. And for this part, as we have done some rounding up and rounding down, actually, the discretized model is not the cannot represent the real case of the continuous model because there are some slack time when we do the roundings. So we use these 2 constraints to ensure that there will not be too much slack time. So the left-hand side basically calculates the total trip time and the loading and unloading time up to each period. And the right-hand side is the total period the total length up to at the end of each period. We ensure that total slack time is no more than two times the length of each period, up to each period. So the other objective function is the user dissatisfaction. So we used a Markov model, which is proposed in ISE in 2017. So I'm not going to details on this calculation. So basically, the dissatisfaction is using a Markov model to model the expected number of users fail to rent or return a bike during a day, given an initial inventory of usable bikes P0 and broken bikes B0. So the first term is this is like the math expectation, probability expectation. I here is the probability, and mu t here is the rent or returning rate. So we calculate how many occurrences of bikes failed to be rent or returned because the station provides 0 usable bikes, or the total inventory at the station is full. So the user cannot return any bikes and in this case. And this number is calculated as a table. So we will see that actually the dissatisfaction at each station is based on its initial number of unusable bikes and initial number of usable bikes. So this table is nonlinear, and the author have proved that a convex polyhedral function can be fitted nearly identical values to the EUDF so that we can incorporate this number into our model with a linearized constraints. So basically it is a U-shaped function, as we see with the increase of, like we see when the number of usable bikes is 0, with the increase of initial number of usable bikes, the dissatisfaction decrease at first. Then at 27, it reaches a optimal value. After that, it increases again. This is because after this number of usable bikes, the station becomes occupied by the bikes. So the returning side is prohibited, affected. So the dissatisfaction start to increase again. Well, for the broken bikes, obviously, the more broken bikes, the larger the user dissatisfaction. So basically, it's a U-shaped function. So the problem's NP-hard, and it is a complex variant of VRP. So for small scales, we use exact method, like Ruby or Cplex as our solving tools. And for large scales, we developed a hybrid genetic search with adaptive diversity control. But we proposed a station budget constraint heuristic here. So the detail of this algorithm, I won't go too deep here. So the characteristic of this algorithm is like in the population, it keeps both a feasible population and an infeasible population. Like the infeasible solution are not just discarded, they are also kept in the solution pool. And for the later local search or repairs, they have the chance to become feasible again. So this guarantees the diversity of the population. So it has already successfully been applied on similar studies. And the procedure of our solution method is we generate route first, then we assign the quantity of the loading, unloading, and repair based on the route, and then we evaluate the objective value based on the loading, unloading, and repair, and the route. So traditionally, many researchers uses greedy heuristic for the determining the number. So like the target inventory of this broken bike is 2. Target inventory of the usable bike is 2, and the current inventory of usable bike is 3. That we need to move. We need to load 1 bike here. So we assume the truck came empty and it will load 1 usable bike. And there are 2 broken bikes marked in red, and they load 2 broken bikes. So this is just load as many bikes as possible when you arrive at station, like given a route A, B, blah, blah, blah. However, this is obvious, short-sighted. It would overinvest research early for like station A. Like for the stations at the end of the route, like the truck would have no space, or we don't have enough reposition budget. This just ignore the fact that the inventory change actually benefits users most, those stations. How does this greedy, why is this greedy not enough? So we see let's see the changes of like 3 stations here on the user dissatisfaction function. So the color represents the heat map of the user dissatisfaction. We see like for this station in the middle, moving 44 bikes, you have a clear change in the color. However, in the station at right-hand side, rightmost picture, you move 41 bikes, but the inventory change is small. You see the color is similar. The variation is subtle. So some stations drops much more as the inventory changes, while some are much less. We should prioritize the actions at stations where small changes yield big improvements in the user satisfaction. So we defined a benefit over cost ratio. Basically is the reduction when you move from the current point to the optimal point divided by the time it consumes to reach such an inventory. We need a CP value. We need a higher CP value to prioritize the stations. And we see like at station 2, it has nearly 10 times of station 3 on the BCRF, while the movement of bikes is quite close. So using this one, when we do the greedy, for the last term, we don't use the maximum number of given remaining time. Rather, we gives larger time frame, larger time duration for the stations with higher BCRF values when we do the calculation. So this is not a greedy guided solution. This is a station budget guided solution. So here is our solution method, our results. For small cases, we use Groovy, and the repositioning time budget is set to 2 hours. No, this is the repositioning budget. It's a model parameter, not the running CPU time limit. And we run this exhaustively, and we see like for some stations, for some case instances, it takes around 4 hours to solve. While using our proposed heuristic, it only requires 3 seconds to reach the same optimal solution. And for large instances, we vary the number of trucks and repairers, and we set the running time limit for both Ruby and our proposed method to 2 hours. And we see that our proposed methods gives at least 17% gap superior to Ruby. And for even larger ones, like over 200 stations network, we see like these cells marked with NA means the memory of 64 gigabytes was running out. So we have nothing to report here, but using our proposed heuristic, we can still achieve somehow smaller gaps superior than Ruby. And finally, we conducted a effectiveness research on the repair times. So we vary the time it consumes to repair a bike from 5 minutes to 20 minutes. And the y-axis here is the gain you obtained after you involve a repair compared with you don't involve, divided by the salary you need to pay for the repair. So it's still also like a benefit over cost, the gain divided by the cost. So for the first two cases, when the L here means the total number percentage of broken bikes in the system, when the total broken number in the system is small, actually involving a repairer is never cost effective, it's cost ineffective. You need to pay more. But starting from 30%, you start to get some values over 1.0, which is the critical point in the subsequent figures. And as the proportion of broken bikes increase, repairers become cost effective, but only if repair times are short enough. Because for the right towards this red point, it's become less than 1 again. And actually this point shifts to longer repair times as the broken bike level rise. This is also explainable. Like more broken bikes, the more tolerance of the repair time makes it ineffective. So when this number is over 10 minutes, the repairers becomes cost ineffective for all the cases. So it gives us some practical advice that first is we should dynamically adjust the number of repairs based on the current system status. It's not always effective to involve a repairer. The second one is we should use flexible repair scheduling, like part-time repairer rostering. Third one is based on the proportion of broken bikes, we should actually invest in preventive maintenance to avoid the system becomes that broken, that damaged. So to summarize, so we propose a new BRP with broken bikes, considering on-site repairs, and we formulated with the MIOP formulation and designed a algorithm with new concept of benefit cost ratio. And the cost effectiveness is analyzed in terms of the repair times. So there are some ongoing research. The first one is not every broken bikes are considered equal. So some broken bikes are very heavily damaged that they cannot be repaired on site. So we should differentiate the broken bike types based on the degree of damage. The second one is just like the previous slide, dynamic deployment of repairers based on system status. So that closes my speech. Thank you for your attention. Questions are welcome.
Thank you very much, Rachel. Let's see if we have any questions for his presentation. If you have any questions related to this presentation, feel free to type your questions in the chat, so we will be able to let the presenter to answer your questions. I don't see any questions in the chat box, so thank you very much. And with that, let me introduce our next presenter. Coming up next, we have Soren Shem from Australia. And Soren, can you hear me? Soren, can you hear me? Yeah. Coming up next, we have Soren to present about the research. Let's see.
Yes,
Soren, can you hear me? Let's see. There. Because our fifth presentation, the presenter won't be able to make it today. That's why we'll just go directly to the sixth presentation as shown on the agenda. But the issue is that, Sharon, are you there? Can you hear me? Ikan, can you hear my voice?
Yeah, I can hear you. And Shua is one of the co-hosts already. But he's not. I'm trying to
It's not.
text him to reach out to see.
Sure, and see if he can return. All right. While we are waiting for our sixth last presenter, so let's see. I want to open up to the audience and see if we have any questions. To the previous, I think in total there was 4 presentations. Each one of them have a very interesting aspect, right? And some of them are studying in the discrete choice model, and we also have the optimization method coming in, and then also machine learning method and techniques. We do have a lot of like a lot of you in the audience. If you have any questions related to the topic or to the technique specifically, feel free to type your questions in the chat. And while we're waiting for our the fifth presenter and see if we can get him back here. Yeah, so that was very interesting. Let's see.
I think
So
he's
Ren, are you
here.
still here? Can you hear me? Ikan, were you able to contact Soren? Because I think he is in this Zoom room, but I cannot hear his voice, or I typed to him, but I couldn't reach him.
Yeah, I got reply from him, and he said he's the last in the presentation list. So, because Sachin, okay, all right, I think he's coming.
Great, terrific. Let's give him a couple of seconds because our fifth presenter couldn't make it. I'm sorry about that. So that's why we will skip the student preference and the pedestrian mobility and campus accessibility and move on directly to our sixth presenter, Soren Shem from from Australia, and we'll be talking about the understanding the reception of the perception of bicycle commuting. Yep. Yes, great. You're back. Terrific. I will just, can you hear me, Sharon?
Yes, I can hear you. I'll be starting my presentation
Terrific.
later.
Yes, of course. And with that, and let's give a virtual round of applause for our last presenter, Sorev, and the floor is all yours.
Thank you, Professor. Hello, everyone. Thank you for joining me today. I'm Saurav Shom, and today I'll be presenting our research titled as Understanding the Perception of Bicycle Commuting Among University Students, Developing Nations Perspective. The other authors to this paper is MD Mustafizur Rahman, and our corresponding author is Fuad Yasin Huda. This study focuses on how university students perceive and respond to the idea of commuting by bicycle, particularly in a city like Dhaka, where traffic congestion, poor infrastructure, and safety concerns make everyday travel a real challenge. Let's start with some background. Cycling offers a sustainable and eco-friendly alternative to motorized transport. While global interest is rising, adoption remains uneven across regions. Urban growth, coupled with rising car ownership, has contributed to a 13% increase in global traffic congestion between 2008 and 2015. High-income countries such as Germany and Japan have responded with effective cycling policies and infrastructure. However, in low and middle-income countries, cycling promotion strategies are still underdeveloped. This gap highlights the need for specific approaches to support cycling as a viable mode of transportation. By 2065, an estimated 60% of the global population will be living in cities, with youth aged 15 to 24 making up a significant portion. Among this group, university students present a key segment of urban commuters, typically characterized by high transport autonomy. Yet in Bangladesh, cycling rates among university students remain strikingly low, just 3%. Despite the growing relevance of sustainable transport, cycling behavior in this student demographic remains largely under-researched. Most existing studies focuses on the general population, often overlooking the unique commuting needs, habits, and constraints faced by the students. This gap highlights the importance of investigating student-specific cycling patterns to inform more targeted and effective transport policies. This study aims to examine the key factors that influence university students' preference for bicycle commuting. It seeks to understand how socio-demographic and travel-related variables shape students' attributes and attitudes towards cycling. Using analytical analysis, the research will measure the impact of perceived benefits, external encouragement, and safety concerns on bicycling behavior. Additionally, the study will identify the most significant barriers and motivations affecting bicycle commuting among students in Dhaka city. Finally, the goal is to generate evidence-based policy recommendation to support and promote cycling within the student population. We used a questionnaire survey collecting data over 6 months from September 2023 to March 2024. Our sample included 288 university students. Among them, 66% were male and 34% were female. To reach participants, we used both online and offline modes. Google Forms shared via social media and university groups, QR code pamphlets distributed on campus, and face-to-face surveys. The survey focused on barriers to cycling, such as poor road conditions, lack of bike parking or secure storage, family support, and safety concerns around motor vehicles. Motivators explored included the availability of dedicated bike lanes, shared sidewalks, bike sharing or rental options, and various incentives. Additionally, the survey gathered socio-demographic data, including age, gender, and personal and household income to support more detailed analysis. Here is a visual representation of our conceptual framework, which outlines the key factors, including student cycling behavior. We focused on 3 main constructs in our framework: benefit, encouragement, and safety. Benefit includes indicator variables such as travel time savings, both on route and in traffic jams, cost reduction, and flexibility in route and travel time. Encouragement covers the presence of bike lanes, bike-friendly paths, and access to bike share service. Safety reflects fear of mixed traffic and perception of infrastructure condition. In our analysis, we examined how these 3 latent factors correlate with each other and ultimately how each one individually affects students' preference for cycling. We also included socio-demographic and economic factors as controls to better understand individuals' difference. We hypothesized these factors are not only individually influential, but also interconnected. This assumption was supported and validated through a review of existing literatures as well. Our modeling used 2-step approach. First, we applied confirmatory factor analysis or CFA to validate latent constructs from related variables. Next, we used structural equation modeling or SEM to examine relationship between these latent factors and observed variables. SEM allowed us to capture both direct and indirect effects among variables. To ensure model's reliability, we evaluated its fit by using multiple fit indices like CFI, TLI, RMSEA, and SRMR. Now, the perception towards cycling barriers among university students. Our data shows that 85% of students agreed poor road conditions deterred them from cycling. Safety concerns are also high, with 64% fearing cycling near motorized vehicles. Family and friend support is mixed. 39% feel supported, while 37% do not. Around half of the respondents point to insufficient and unsecured bike parking as a barrier. Interestingly, only 17% expressed a dislike for cycling itself, indicating the barriers are mostly external. The benefits of cycling are clear from our data. 92% agree it helps avoid traffic jams, while over 70% find cycling comfortable and appreciate the flexibility in travel time and routes. Additionally, 93% agreed that cycling saves travel costs, and about 56% felt it enables fast and easy journeys. Our survey shows strong support for infrastructure and services to encourage cycling. 86% favor separate bike lanes and 78% support widened footpaths with cycling facilities. 74% are interested in bike sharing on rental services, while 75% supported special incentives. And last but not the least, over 60% expresses interest in electric bikes. Safety is a major concern for cyclists. 88% agree that helmets should be mandatory, and 80% support the use of high visibility vests and front and rear lights for night cycling. However, only 36% feel confident and unafraid while cycling, whereas 39% expresses concern about potential injuries. Our CFA identified three key latent constructs: benefit, encouragement, and safety that we took in our analysis construct. Benefit showed a strong reliability with an alpha of 0.80 with freedom to choose travel time as its strongest indicator. Encouragement had an alpha of 0.77 led by the presence of separate bike lane. Safety showed moderate reliability at 0.60 with unfavorable roadway condition as its strongest factor. The model fit was excellent with CFA at 0.95, TLI 0.93, RMSE 0.03, and SRMR 0.05, indicating a robust measurement model. Now on to the SEM results. Our SEM results reveal some interesting patterns. For travel distance, those commuting 10 to 15 kilometers are more influenced by benefits and encouragement factors. However, longer travel times, around 1 hour or more, reduce the influence of all factors. Regarding monthly travel expenses, participants spending 10,000 to 15,000 BDD, which is equivalent to $1,100 to $150, strongly influenced by benefits. Travel modes also matters. Walking and bus commuters are less affected by benefit factors, while those who commute 4 to 5 days a week show greater influence for encouragement. Experience plays a role too. People without bike theft experience are less influenced by the encouragement factors, and experienced riders who already know how to ride a bicycle are more concerned with safety. Our SEM results reveal interesting relationships among latent variables. Benefit and encouragement has a strong positive correlation, as do encouragement and safety, while benefit and safety show no significant link. Looking at the effects on bicycling commuting preference, perceived benefits have a significant positive impact on cycling preference. As benefit increases, so does the likelihood to choose cycling. Encouragement has a negative but not statistically significant effect, suggesting it may positively influence cycling preference, but this was not confirmed in our data. On the other hand, safety concern strongly and significantly reduce the preference for bicycle commuting. The greater the safety concern, the less likely students are to cycle. In terms of model fit, the indices indicate an excellent fit, with CFI at 0.99, TLI 0.98, RMSE 0.01, and SRMR value of 0.03. To conclude, our study highlights several key findings. Travel distance and economic factors strongly influence cycling preference, with longer commutes increasing the perception of cycling as a cost-effective and time-efficient option. Safety concerns, including fear of injuries and lack of riding experience, remain major barriers to cycling. Meanwhile, improved biking infrastructure, such as dedicated bike lanes and widened footpaths, plays a significant role in encouraging cycling adoption among university students. Now, on to policy implications. First, improve cycling infrastructure by prioritizing dedicated bike lanes, bicycle-friendly footpaths, and secure parking, especially along medium-distance routes where students are more responsive to cycling benefits. Second, the university should step in with student-focused support, like provide bike sharing programs on campus, offer basic safety training, and run cycling awareness campaigns. help students combine cycling with public transport by making it easier to switch between modes can help a lot. E-bike sharing can also help with long distance commuting by reducing fatigue. And finally, offer financial incentives like discounts on bicycle or e-bike share membership, especially for students with higher travel costs. This can make cycling a more practical and attractive option. Our study has some limitations. Our study, since we relied on self-reported data, there may be some bias, particularly in how students perceived benefits and safety. Also, because the study was conducted in Dhaka only, the findings may not be fully generalizable into other contexts. For future research, using reveal preference or longitudinal methods could help reduce bias and better capture changes in cycling behavior over time. Comparing results across cities with different cycling infrastructure would offer valuable insights as well. Additionally, future work could explore how peer influence, institutional policies, and social norms shape commuting choices. It would also be useful to examine which benefits like cost savings versus time flexibility matter most to the students, and which infrastructure improvements have the strongest impact. The takeaway from this study that by addressing safety, improving infrastructure, and tailoring policies to students according to their financial and travel policies, we can move closer to a more sustainable urban future, even in the global south. And that's all from my presentation today. Thank you everyone for joining. I would love to have any questions or insights you may have regarding this research.
Thank you very much, Saurabh. Let's see if we have any questions for you in the chat. And we also opened up for all questions to all our presenters for today's section. If you have any relevant questions related to the previous 5 presentations in total, feel free to type your question in the chat. Mm-hmm. Oh, just while we are waiting, some of our audience, some of you in the audience may be typing your questions there. I just want to let you know that our Bridging Transportation Researchers, the conference actually have the Eastern track and the Western track. So if you're interested in the Western track, the headliners presentations, you can also stay up late and join around 11. That's 11 p.m. in China. I think for Australia, but then so this is the Eastern track, the end of day 1, and then moving on tomorrow we will have the second day in the Eastern track, and we will kick off with the headliner Professor Yi Qiu Tan from the Harbin Institute of Technology Weihai campus. She's also the president of the Weihai campus. So we look forward to seeing you tomorrow morning in the Eastern track with the kickoff headliner presentation. And with that, thank you very much for today's presentations and for being here with us today. And let's see if we have any questions in the chat for the very last track. Oh, I do have a question here. Let's see. So I think this is a question to you, right? Saurabh, are you still here, Saurabh? Let's see, regarding bike commuting, did you reconsider if cyclist is the owner of the bike or just a rental? Does it affect decision making? Any thoughts on that?
We had a question regarding that in our survey, if the student own a bike or not. But in our analysis, we found that it was not significant. That's why we actually didn't count it in our paper and in the presentation here today as well.
Okay. Yeah, thank you. All right, so I don't see any more questions in the chat. Thank you very much, Saurabh, for answering the questions, and thank you all for being here today with us. Thank you to our Zoom coordinator, and thank you for all the presenters. That's the end of today's section. We look forward to seeing you tomorrow morning. Yeah, with that, bye and have a good day.
Thanks.